The contributions of this work are threefold. First, we introduced the novel task of identifying a 3D object in a real-world scene given a description of it in natural language. Second, to solve this task, we create two physiolinguistic datasets with discriminative utterances describing objects in 3D scenes. And last, we develop a multimodal deep neural network that comprehends references made about these objects in order to identify them. For the aforementioned problem, we make two important design choices. First, as shown in this image, the referred target, here a table, must coexist in the scene with multiple distracting instances of the same class in addition to different class distractors. Second, we ground our problem directly in 3D space, and specifically, we use 3D point clouds to represent the scenes and their objects. To build our visual data, we consider more than 700 scenes from the scanned dataset and 76 fine-grained target object classes to create scene target tuples, which we term communication contexts. These contexts are of varying complexity, with the easiest one containing one intra-class distractor and the hardest one up to 5. Considering how to build linguistic references for those visual data, we define the following two properties: view dependency and scene discoverability. Regarding the view dependency, observe how a reference can change the indicated target according to the spectator's viewpoint. To make such an utterance uniquely refer to a target object, one needs to also describe the used viewpoint. Regarding the scene discoverability, even if the utterance allows one to identify the target among the same class instances, it might not be sufficient to discover that target within the entire scene. An easy fix for this problem is to mention the target object class or a synonym of it. To collect natural language data, we deploy a reference game between two humans. First, a human speaker observes a 3D scene that contains a designated target and its distractors and is asked to provide a discriminative reference for that target. This reference is then used by a human listener who, given the same scene, is asked to identify the target among the same class instances. The resulting dataset contains more than 40,000 utterances, and human listeners were able to accurately identify the target 92.2% of the time. Perhaps more surprisingly, 91.6% of the time, the speakers made references that were scene discoverable. Another key finding is that spatial reasoning is ubiquitous in these utterances and much more frequent than the use of color or shape attributes. Following this insight, we augment our natural utterance dataset with synthetic utterances that express spatial reasoning. Specifically, we create a corpus using a compositional template that considers 5 broad types of spatial relations among 3D objects. We note that the generated utterances aim to unambiguously distinguish the target from its intra-class distractors by considering its spatial relations with other anchor objects of the scene. Here are examples of the generated data. The resulting dataset contains more than 80,000 discriminative utterances that are useful both to humans and neural listeners. In a conducted study with 2,000 sampled utterances, human listeners identified correctly the target object 86% of the time. We also observe in our experiments that augmenting our natural data with the template-based references is resulting to improved accuracy. Before we describe ReferIt3D net, we discuss baselines. The simplest one is comprised by a text classifier that predicts for a given utterance the target's object class. At the same time, an object classifier predicts the object class for each 3D point cloud instance in the given scene. We couple the two classifiers by outputting the object for which their predictions agree when multiple such objects exist. We pick one uniformly at random. The most important part of this experiment is to understand how these two essential building blocks for our downstream task perform individually. Namely, we found an asymmetry. Referential text classification appears to be much easier than 3D fine-grained object classification. We next consider how to create a neural network that predicts a compatibility score between the input utterance and every object of a scene. Given a 3D object, we extract its visual feature and use it to ground a language encoder that processes the input utterance. We repeat this step for all objects in the scene and use an MLP classifier to predict the target given each individual derived representation. We note that this is a context-free neural listener that does not explicitly consider interactions among the objects of the scene. A simple improvement to the previous shortcoming is to give as additional grounding information a feature extracted from the entire 3D scene in an unstructured manner which does not explicitly take into account individual object instances. While this feature can enable learning interactions among the objects, it still provides context only implicitly. In our proposed architecture, we combine language with vision differently than what we have presented so far. Specifically, after we extract the visual features of each object and a linguistic feature for the utterance, we fuse them via a dynamic graph neural network that takes as input their concatenated representations and explicitly encodes pairwise object interactions among objects that are nearby in a latent space. The final fused representations are passed to a shallow MLP that predicts the target. For this architecture, we also use two auxiliary classification losses that guide the visual and linguistic representations to solve the tasks shown in our simplest baseline. Our main findings are the following. The explicit context incorporation in ReferIt3D net gives a boost in the performance with respect to the less context-aware baselines of about 7%. Using the two auxiliary losses in ReferIt3D net improves performance by up to 3%. As expected, ReferIt3D net performs better in easy contexts than hard, but also does better in descriptions that do not refer to a target in a manner that relies on a single specific view. We also observe that training with both natural and template-based spatial utterances is beneficial when testing generalization on natural references. Last, we saw that using the SR3D data during training in the pipeline of a concurrent work on object localization can be beneficial in terms of the achieved mean IOU accuracy. Following are qualitative examples of applying ReferIt3D net on natural utterances. Here, we saw successful cases on NR3D. We would like to emphasize that these examples are challenging since they require spatial, color, and shape understanding, as well as due to the presence of more than one distractors in the scene. The illustrated probabilities are the neural listener's confidence score, and note that we omit those of interclass distractors. We also saw two characteristic failure cases. The first example shows a scene with pronounced symmetries, which makes the problem very hard even for humans to describe and solve. The second example shows how complicated human reference can be, as in 12 o'clock from the poster. Here we saw successful qualitative cases of SR3D in easier contexts. Aside from the listener being able to identify the target, we note that our utterances are human-like and rich. The failing examples in SR3D are mostly associated with objects that are very close in 3D space to the target, making identification more challenging. Our presented approach is still far from achieving human-level accuracy. We think that in the future it will be interesting to investigate more modular listeners and tap on 3D attention and perhaps have some form of viewpoint awareness. Regarding the data, we believe that having more novel scenes could be very useful for learning purposes. Also, one could utilize information about object shapes and colors to create other type of referential utterances in a manner similar to what was done in SR3D. For more details and results, please visit the project's webpage. Thank you for watching.